Okay, so we finally made it to 3D. And so similar to 2D, right, we have a tetrahedron and a hexahedron. So our transition from 2D to 3D is going to be pretty straightforward. The hexahedron sometimes gets called a brick. So like in our software, it refers to it as a brick instead of hexahedron. And again, like in the 2D mode, we didn't use, or the tetrahedron wasn't used very often. We don't use it very often in 3D either. It gets used occasionally for transitions or type radii maybe. But for the most part, we end up using hexahedrons. Now, 3D is certainly a little more complicated, takes a little more effort, certainly takes more analytical power to calculate and determine it. So to help us out and ensure that we're going in the right direction, that we have good values from our 3D model, it's always an excellent plan to do a 2D approximation of your 3D solution, if for no other reason than to give you the limits, the boundaries of what your 3D should land in between. I mean, the images up here, obviously this one's fairly easy to do as a 2D model. Just take the profile and do it that way. This one, a little more problematic, maybe not so simple to determine. Maybe you do a 2D profile of just this lower part to give you the lower limit. Your 3D model should end up above that. I don't know how this is loaded or constrained. I mean, we can make assumptions about it, but it's, you can still come up with an approximation. And like we did in 2D, we want to try, if we can, to take advantage of symmetry when we're dealing with 3D, cut down on the processor time. And I think we were able to prove with the 2D that the symmetry gives us a pretty good approximation of doing the full model. And we can often get to the solution quicker with the symmetry than we can with the full model. Also, in the software, there'll be a mesh checking button. It's not a bad, when you hit analyze, it does the mesh check first, but for complicated parts, it's probably not a bad plan to do the mesh checking ahead of time. So if there's some issues, it can highlight that. One of the things that it's checking for, when you have all these different size shapes, and making sure that you have no distortion issues, and it's also going to look for free edges, so some micro voids, because we can't tell what's going on inside. All we see is the surface mesh, so it's checking the inside for voids. So on a larger, more complicated model, good idea to do that before you tell it to analyze, just to make sure everything's okay. So they had a case study for this chapter, and it's a short beam and it's wide, so that violates a lot of our assumptions of simple beam theory, right? Because we're talking about small cross-sectional area compared to the length, and we also say that shear is inconsequential compared to the bending. And we talked about that previously and had a graph for that. But just to see what's going on and what the software is going to do, this beam's 5 inches long, 4 inches wide, 1 inch thick. It's constrained on the end in the YZ plane. The length of the beam runs along the x-axis. And the model depicted here is a half model, so it's 2 inches wide instead of 4. and the load is on the edge, where it's an edge loading totaling 1,000 pounds on the top nodes of the end plane, the free end, where the blue line is, and it's has symmetry about the XZ plane, right? So you have no translation in the y-axis. So when we're looking at the software, it has symmetry buttons for the constraints, right? So when you're thinking about symmetry or determining what your symmetry is, you have to look at the plane that your surface is in. So in this example, our plane is the XZ plane, and so we know that our object is being mirrored about that plane, or the x-axis, if you will. And so anything normal to the XZ plane is symmetrical, right? So that's why the software calls this Y symmetry, because anything along the y-axis in either the plus or y direction is symmetrical about the XZ plane. Okay. So since I cut this model in half, and the XZ plane is my axis or my plane of symmetry, so I have my normal axis is the y, so that's my Y symmetry. That's how it's defined in the software. Okay. So we have an edge load out on the end, 1,000 pounds. So when we run the model, we would expect, if we're looking at it from the XZ plane, we would expect some sort of deflection like this. And surprise, surprise, that's what we get in the software. But if we look at it in the YZ plane, this is showing that it's wanting to curve, not stay. So this is the cross axis, right? We're not looking, we're cutting through this and looking at the YZ plane, right? So we're on the x-axis looking towards the YZ plane, right? That's what this is. And we can see that it's kind of curving a little bit. Does that make sense? Can we explain that? Is that, well, is it explainable? And the answer would be yes, because we're dealing with a short beam, right? So our shear in the beam is going to play a role in the deflection that happens in the beam, because we're dealing with short beams. And if we look at our model, not the best picture, but it's definitely behaving similarly and curving on the outside edges. So shear does happen, does play a role in our beams when they're short. And we remember from that graph that I showed last week or so, until you get out to about a 10-to-1, 10-to-1 aspect ratio, shear plays a role in your solution. So be aware of that. That was kind of my summary. Anyway, so that's 3D.